Thank you for joining us. We're going to give it about 1 more minute just to let everybody trickle in, and then we will get started. All right, so we are going to go ahead and get this webinar started. Hello, everyone. On behalf of the Environmental Finance Center Network, welcome to our webinar today on activated sludge process control calculations. My name is Maya Bani from the Syracuse University Environmental Finance Center. And before we begin, we're just going to go over a few housekeeping items and then we can get started. During the training today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar questions dialog box anytime throughout the session. After the webinar, you will receive a follow-up email that includes a link to this recording and any other information you may need. You can also download the slides today in the Handouts tab in your GoToWebinar control panel. This session has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of this webinar date. If you have any questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us, the Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I'll be sharing shortly in the chat. And on that note, we can get started. I would like to introduce our presenter for today, Gregory Pearson, a water and wastewater trainer at the Great Lakes Environmental Infrastructure Center at Michigan Technological University. And Greg, just give me 1 moment and I will transfer this over to you.
Great, thank you, Maya. Did it seem to work, Maya? Do you see my screen?
Yep,
now?
I can see your slide deck.
It says what we will cover today?
Yes, it does.
Okay, great. Thank you very much. Welcome, everyone. Glad you're here today with us. And I'm going to go over what we're going to cover today, and then we'll get started. First of all, we're going to start with, with an overview of the activated sludge process. And then we're going to go into the 2 equations that we're going to focus on today. The mean cell residence time formula, which gives us a result in days. We're looking at the pounds of mixed liquor suspended solids under aeration divided by the pounds per day of solids that are leaving the system. And then the second formula is the food to microorganism ratio. it gives us kind of a, we consider it to be kind of a dimensionless or a unitless ratio of the food to the microorganisms in our aeration system. Activated sludge plants, it's very difficult to apply a one-size-fits-all method of process control, but there's some things that are constant. These two equations, these two formulas, mean cell residence time and food to microorganism ratio, it is useful even if you have a very different type of activated sludge plant. You could have extended aeration or high rate activated sludge, and these two equations will still help you to figure out how to control the process. All right, let's go to our first poll. And Maya will, I think, will bring that poll up. And it's basically asking which statement best describes your learning goal today.
All right, the poll is live, and these will be up about for roughly a minute or until I see most that everyone has answered the poll, and then I will close it out. All right, I am closing the poll in 3, 2, and 1. All right, so it looks like, all right, our highest percentage, 43%, said something else, make a comment. So let's see what people are saying in the box here. I see they're a finance officer trying to learn about wastewater systems. They are state regulators, a bunch of state regulators coming in here. And then 29% had responded that they are an experienced operator, refreshing my understanding of ASPC. They are a new operator, that's 9%. 16% had said that they are preparing for an upcoming certification exam. And 4% had said that they are a board member seeking insights for a future or upcoming infrastructure project.
Great. What a great mix of attendees today. We're glad you're all here. For some reason, my PowerPoint keeps on popping off of presentation mode for some reason, Maya, so bear with me, everyone. So why are we gathered here today? Well, the main focus today is we're going to look at the FM ratio and the MCRT formulas so we can use them as part of activated sludge process control. But there's some other questions that will probably pop up as we're discussing this, especially with people that are just learning about this. The first is, what does the results of these formulas mean to us? I mean, if we have an FM ratio of 0.1 or 0.5 or 0.3, what does that even mean? And also, if we have an MCRT of 3 days or 15 days or 20 days, what does that mean? What data do we need to put into the formulas, and how do we obtain it? And after we evaluate the formulas, how do we actually adjust the activated sludge process? So I'm hoping to also answer those types of questions as we proceed through this training. And you know, we're kind of disconnected from each other in this webinar platform, and it's a very short period of time that we're spending together. But I want to encourage you to, as we work these problems and some of the associated sample calculations, work them with me, please. Get out your calculator and a notepad and take some notes. You might even be able to catch a mistake I make. Also, if you have any questions, please put them in the platform and respond to the poll questions. Thank you for participating in the poll we just had. All those will help you get the most out of this training. So let's start with a little overview of the activated sludge process. And just a general comment before we start. Activated sludge was really developed in the first couple of decades of the 1900s. And there was some dead ends and some misstarts. They didn't really understand what was happening on the microbiological level when they first started experimenting with it. But wastewater treatment in general, and especially activated sludge, has made a major impact on human health and environmental health throughout the world. If you list the things that are most significant to human health, if you listed all those top things, penicillin, different types of medical treatments, disinfection, activated sludge would be at least among, if not the top of that list, on impacting human health, preventing disease transmission and protecting receiving waters. If we look at an overall kind of a general layout of a wastewater treatment plant with activated sludge, we have our preliminary treatment, which you screen and rags and solid floating objects and get rid of grit. But we enter treatment first in the primary clarifier. What does primary clarification do? Well, it allows the solids that are already ready to be settled to the bottom of the clarifier and removed. And the liquid above that is clarified continues on as the primary effluent into the activated sludge process, which consists of the aeration tank and the secondary clarifier. It's important to remember that what's entering into the aeration tank is those solids that are not readily settleable. They're not going to settle without some sort of treatment. And these non-settleable solids consist of waste that would be hazardous to the environment. It would be a problem if they were in the environment. So something has to happen. We're going to bring these waste, this BOD, into contact with microorganisms in this process, which will consume the waste and convert it to cellular biomass. And we're going to zoom in on that activated sludge portion now, which we're looking at just the aeration tank, the secondary clarifier, and the return activated sludge flow. In this diagram here, we have the effluent. We call it primary effluent because it's coming from the primary clarifier, and that's bringing BOD and waste into the aeration tank. The secondary clarifier is where the microorganisms, basically the biomass, is settled in the secondary clarifier. So that's basically collecting the microorganisms, and then you have the return activated sludge flow, which recirculates a portion of that biomass back to the primary effluent. And so what you're doing here is combining the eaters and the food together in the aeration tank. When you combine the return activated sludge flow and the primary effluent, you get what you call a mixed liquor. It's mixed liquor is consisting of BOD, inorganic particles, and organic particles, which mainly consist of microorganisms. So in the aeration tank, you can consider that kind of like the dining hall. You're converting BOD to biomass. The secondary clarifier is kind of a temporary holding tank where the biomass is collected, ready to be either recirculated or eliminated from the system as waste-activated sludge. Some waste-activated sludge is always being eliminated. These are all continuous flows to maintain a solids balance, and the return-activated sludge flow is so that you can bring microorganisms to consume the waste. If we look at just the aeration tank, what's going on? You have the food coming in the form of BOD and the incoming wastewater. You have the hungry organisms coming in as the return activated sludge to make that mixed liquor, and you have aeration. Maya, is the audio coming through okay?
Yep, you sound great.
Okay, I got a little notification here that about network difficulties, but I hope everybody can hear okay. Now here is an actual photograph of a aeration tank. This is at the beginning of the tank. You see the primary effluent coming in. That's the effluent from the primary clarifier, remember? It looks relatively clear compared to that return sludge. It's settled sludge, so it's somewhat thickened. And it's bringing those microorganisms back to the beginning of the aeration tank. So the eaters and the food are being combined together, and air that's necessary for the metabolism is also being added. You can see that surface is churned by the aeration that's going on. The aeration helps to suspend those particles and to mix the return sludge and the primary effluent and add the necessary air for metabolizing the waste. As the waste enters, this diagram here is a tank with the beginning of the aeration tank on the left-hand side. As we first enter the aeration tank, where those two flows were coming in, there's a lot of bugs and a lot of food. So the microorganisms have a lot of food and the oxygen demand is very high. But as the food is consumed, as we go through the tank, from one end of the tank to the other, the oxygen demand goes down. So you have a lot less oxygen demand by the end of the tank, and that's because at the end of the tank, you pretty much have almost all of the waste has been converted to cellular mass of bacteria and xylates and other microorganisms. And that flow then goes into the secondary clarifier. Here's an image of an actual secondary clarifier, circular clarifier. And the purpose of a clarifier is to slow down the flow so that suspended solids that are settleable will settle out, and the clarified liquid on top will continue on toward the effluent. So let's look at the secondary clarifier flows. You have the mixed liquor being discharged from the aeration tank. By now it's pretty much cellular biomass, which settles. And you basically have a sludge that consists mainly of hungry microorganisms. About somewhere between 0.6 and 0.8 of that sludge is microorganisms. You also have the return flow that's going back to the inlet of the aeration tank, and you have the waste activated sludge that's being sent to solids handling. Okay, and finally the effluent. If we look at a typical activated sludge process here, you see the plant flow coming in from the left there. That's the liquid flow, and it continues through the aeration tank to the clarifier and out through the effluent. You have air coming in to the aeration tank, high oxygen demand at the beginning, low oxygen demand at the end, like we saw. And then we have our sludge flows, a return activated sludge coming to the inlet of the tank, and then our waste activated sludge, getting rid of solids. Now, the aeration, the time that the liquid mixed liquor spins in the aeration tank, it is a shorter time than the MCRT. We're looking at between 2 to 5 hours, depending on the plant design. And the liquid portion goes through relatively quickly compared to how long the solids remain. In general, for activated sludge plants, the solids remain anywhere between 3 to 15 days. Some sources say 5 to 15 days, but that doesn't mean that's the range for any one particular plant. That's the range of all the different types of designs for different types of activated sludge layouts. And I'm showing you the most simplified diagram of an aeration tank, where all the loading is at the beginning and it continues to the end and then to the clarifier. There's lots of different ways that these things can be fed, but this is the simplest way to show it. The concept is the same, but just know there's lots of variation. There's step flow, for example, different kinds of ways that it can be fed. Still, the F-M ratio and the MCRT that we're going to look at today, it's still relevant to all those different variations of activated sludge plants. Let's go to poll 2 now, and we're going to ask a question about what's the next most important step for the wastewater system in your community. And it could be the wastewater system that you work at or manage or just live in the community with.
And again, this will be up for about a minute. All right, closing the poll in 3, 2, and 1. All right, our leading answer with 37% responses upgrade the wastewater treatment plant. The next 31% replace or rehab collection system components. And then we have a tie to 12%ers here. The first one is assess the condition of wastewater pipes. Next one is extend service to unsewered residents. And then lastly, with 7%, we have conduct a rate study and develop a CIP.
Excellent. Well, thank you very much, Maya. And I realize that probably all of those needs are probably going on concurrently in your different systems, but those are all important strategic goals that you're dealing with there. Let's move on to the first formula, which is the mean cell residence time. This is the average length of time in days that the biosolids are retained in the aeration system, in the aeration tank, clarifier, and return activated sludge. So while the liquid part just goes right through and exits as effluent, the sludge may go around this little ride several times into the aeration tank, settle in the clarifier, return as the return activated sludge, and it might do it quite a few times. The general formula for MCRT is the pounds of mixed liquor suspended solids under aeration divided by the pounds of suspended solids that are wasted per day. So you see in this equation that the waste activated sludge has a big impact on the MCRT. As solids remain in an activated sludge system, they'll begin to get more and more complex. Very old sludge can take on a different kind of a biome. You get more complex and larger organisms after a time. What's difficult is if you have a conventional activated sludge plant and you start getting a lot of complex organisms and you're trying to process waste relatively fast, some of those different types of organisms can disrupt settling, for example. So there's a lot of kind of fine tuning to do. Whereas in an extended aeration plant where you're holding solids for a lot longer, you're expecting that more complex wastewater sludge biome. So the solids under aeration, sometimes it's in certain equations, certain applications, we're just dealing with solids in the aeration tank. And in other applications, we look at the solids in the aeration tank and the clarifier. Both are correct as long as you use them consistently. If you're trying to do process control, you wouldn't want to do on Tuesday, you do a calculation with just the aeration tank solids, and then on Wednesday, you do a calculation with the aeration tank and the clarifier solids. The main point here for using this for process control is to do it the same way every time. In some cases, if there's more than one clarifier and the sludge blankets are different depths and so forth, it really makes sense to keep track of the solids in the clarifier. But we're going to look at both ways of doing the equation, okay? And then, of course, you're dividing by the solids that are wasted as waste-activated sludge. So let's do a simple example. A wastewater treatment plant has a total of 36,000 pounds of mixed liquor suspended solids under aeration, and we're getting rid of 3,000 pounds each day as waste-activated sludge. What is the MCRT in days? Well, pounds under aeration is 36,000. Pounds per day wasted is 3,000 pounds per day. If you invert and multiply that pounds per day, the pounds cancel, and you're just left with days. Anyone have the answer? You can put it in chat if you see the answer.
I see an answer of 12.
Excellent. You get an A+ for that answer because 36,000 pounds divided by 3,000 pounds per day gives us 12 days. So that's the simplified version. Now, we're going to need to use the pounds formula normally to actually arrive at the number of pounds that are under aeration and the number of pounds that are being that are leaving the system. So let's look at the pounds formula real quick. Pounds equals million gallons times milligrams per liter times 8.34 pounds per gallon. This is the formula that we use to kind of convert between the concentration of solids in milligrams per liter, which is the same as parts per million, and the weight of solids in pounds. So it's equally useful to have the concentration and the weight in pounds when we're doing this weight-activated sludge math. mg means we don't use gallons, we use million gallons. So 1,000,000 gallons, 1 million gallons would be 1.0 mg. Let's do an example here in a second, but the units of volume or flow is mg or mgd, concentration in milligrams per liter or parts per million. 8.34 pounds per gallon is the weight of 1 gallon of water. And your answer here, what we're solving for now in this formula is pounds or pounds per day. And we can solve for different aspects of that if we rearrange the formula. Here's an example. How many pounds of suspended solids are in an activated sludge aeration basin if the volume is 800,000 gallons and the mixed liquor suspended solids concentration is 2,000 milligrams per liter? Well, right away, we're going to have to do a little conversion with that 800,000 gallons, right? We can either divide by a million or we can move the decimal place to the left 6 places, but that's going to end up being 0.8 million gallons. Does everybody see that? So we're going to use 0.8 as our mg times 2,000 milligrams per liter times 8.34 pounds per gallon. Anybody want to run that equation, run that calculation?
I'm seeing 13,344 pounds.
Excellent job. And that's what I got as well. Now let's try an MCRT actually using the pounds formula. And we're going to keep it simple also on this one. We're going to just use the aeration volume for this one. We're not going to include the clarifier in this particular one. And we will do one that's the complete MCRT as well. So here we have, what is the MCRT in days for a wastewater treatment facility with the following parameters? Aeration volume, 2 mg, 2 million gallons. And the mixed liquor suspended solids, 2,400 milligrams per liter. The waste activated sludge flow is 0.15 mgd, and the concentration of that sludge is leaving is 6,400 milligrams per liter. So it's quite a bit more concentrated. We're going to have 2 pounds formulas, one for the top, for the solids under aeration, and one for the bottom, which is the pounds per day that are leaving the system. So let's set that up. The pounds under aeration, okay, 2 mg times 2,400 milligrams per liter times 8.34 pounds per gallon gives us 40,032 pounds under aeration. And now, then we'll look at the bottom of the equation, the pounds per day that are wasted. We have the sludge flow of 0.15 mgd times 6,400 milligrams per liter times 8.34 pounds gives us 8,006 pounds per day being wasted. So can anyone tell me the number of days they think this MCRT is going to end up being?
I see a bunch of answers for 5 days.
Excellent, excellent job. So if we divide 40,000, basically 40,000 divided by 8,000, just to say it in rough figures, gives you about 5 days. Excellent job.
Greg, I have a question in here for the previous equation.
Yes.
Someone is asking if you can go over the units in the previous equation. They're asking how do they cancel out?
In the pounds formula?
Mm-hmm.
In the pounds formula, is that correct?
They're asking how do you get to gallons at the end when you have milligrams per liters in millions gallons.
Yeah, I would normally go over that, but in a short webinar like this, I can't really go into the pounds formula, but in too much detail, we just have to accept that it works for now. But if I'll put my email at the end, and please feel free to email me, and I will send you more information on the pounds formula. But basically, million gallons, think of that as million, and the milligrams per liter, think of that as you're dividing by a million, because it's 1 part per million. Million per part on the flow or the volume, and 1 part per million. So those things kind of conceptually cancel out, but it's a little bit strange. The pounds formula is a little strange. It works though. So just send me an email, and so we don't take up too much time. It's a good question and it's a fair question, but anybody who wants to know more information about that pounds formula, I will send you by email. Is that fair?
Thank you, Greg. Yes.
Okay. So like we said before, the waste activated sludge flow has a significant effect on the number of days that solids remain in the system. As we see here, just a little simple example. If we had 20,000 pounds under aeration, 4,000 pounds per day leaving, our MCRT would be 5 days. If we increased that waste flow to 5,000 pounds per day without changing the solids under aeration, it would our MCRT would go down to 4 days. So you see, it has a fairly significant effect. Now, normally you would see the formula list the volume of the secondary clarifier and also account for the solids that are leaving in the effluent. After you've treated the waste, the liquid effluent that's clarified, the final effluent, will still have a small amount of solids in it, even a small amount of BOD. So you have to account for those solids going out, as well as the waste activated sludge flow that's leaving. Remember, the equation is solids under aeration divided by the solids that are leaving the system. So in this case, we can look at the total pounds of solids under aeration as the volume of the aeration tank and the clarifier. For the solids that are leaving, we can account for solids in the effluent, as well as the solids leaving as waste activated sludge. And I'll show you an example here, I think. There we go. So keep in mind, here's our basic equation, pounds of solids under aeration divided by the pounds of solids leaving the system. But when we account for all of those factors, the equation looks like this. It's basically 3 pounds formulas. The pounds formula on the top is the aeration and the clarifier volume times the mixed liquor suspended solids. It's the same solids concentration for both. It's just that the clarifier is settling, whereas the aeration tank is mixing. On the bottom, you have a pounds formula for the waste activated sludge flow and a second pounds formula for the suspended solids in the effluent. Let's look at this here, the top, the solids under aeration, solids leaving as waste, WAS, and solids leaving in the effluent. I'm going to give you an actual a problem here. And it looks complex, but it's not really complex. It's just 3 pounds formulas. You will use up a whole sheet of paper sometimes figuring these out, but it's not that it's so complex. It's just long. So first of all, let's look at the top of our formula there. We got the aeration tank and the clarifier volume, and that's right here. Aeration tank volume is 1.0 million mg, and the secondary clarifier operational volume is 0.25 mg. So you have a total volume basically of 1.25, okay? And the mixed liquor suspended solids is given to us here, 2,050 milligrams per liter. We'll put that in, times 8.34. So that's all of the solids under aeration. If we look at the solids that are leaving as waste activated sludge flow, we have the flow as 0.055 mgd, and the concentration is 7,980 times 8.34. That's going to be on our bottom. That's leaving. And then finally, the solids that are leaving in the effluent, we use the plant flow. As remember, flow is continually coming into the end of this, into the entrance of this system, and it's continually flowing out. The influent is 3.25 million gallons per day, and the effluent is 3.25 million gallons per day. So 3.25 times the suspended solids of 21.2 milligrams per liter times 8.34. So you multiply those all out, and you get a total solids of under aeration of 21,371 that are under aeration and 4,235 that are leaving. And what do you think the MCRT is? What would you guess it is, unless you calculated it? What do we have in MCRT here? How many days?
I'm seeing an answer of 5.
Yeah. All our answers are 5 today. If you just answered 5 to all the questions, you'd get 100% today. Let's do a third poll. For this one, you can just put a letter, one of the letter in the chat. So we have an activated sludge plant that has 30,000 pounds of MLS under aeration and a wasting rate that eliminates 6,000 pounds per day from the system. What is the MCRT? Remember what I told you? If you just answer what, you get 100%? Well, in this case, it's also true, because 30,000 divided by 6,000 equals what? What do they say, Maya?
They are saying there's a bunch of 5s in here, 5 days.
We have a genius selection of attendees today. Let's move on to the food to microorganism ratio, our second equation that we're going to look at. And that's measuring the food that's coming in as BOD into the influent of our system. That's that primary effluent that's entering the aeration tank. And our microorganisms are the pounds of mixed liquor volatile suspended solids, or the microorganisms that are in the aeration tank. The mixed liquor volatile suspended solids or somewhere between 0.6 and 0.8 of the mixed liquor suspended solids. That represents the microorganisms, the portion of the mixed liquor suspended solids that's the microorganisms. So we have the FM ratio is really dimensionless, really. The incoming BOD divided by the MLVSS is, once again, 2 pounds formulas. We have the plant flow times the BOD in milligram per liter times 8.34. And on the bottom, the volume of the aeration tank multiplied by the milligrams per liter of the mixed liquor volatile suspended solids times 8.34. So a lot of pounds formulas in this training. There's 2 things we need to know for the FM ratio. We need to know the biochemical oxygen demand. We need to know what's the concentration. And we need to know the mixed liquor volatile suspended solids concentration. So we're going to look at each of those things right now. So the biochemical oxygen demand is the strength of the wastewater in milligrams per liter of BOD. What does that really measure? It's measuring how much oxygen is required for the microorganisms to metabolize waste. When the microorganisms consume waste, they use oxygen to oxidize or metabolize. And then that waste becomes their biomass, their cellular mass. It's a 5-day test. So basically you add a sample to a 300 milliliter BOD bottle and you look at the initial dissolved oxygen content and the final oxygen content, and you figure out how much oxygen was used. I'll give you an example here, a simple example. Let's say if you use pure wastewater, it would probably just use up all the oxygen before the test was done. It would be kind of meaningless. But if you use a smaller sample, like for example, a 10 milliliter sample of wastewater, and the rest of the water, the rest of the 290 milliliters is some type of pure water, you'll have a better result than you just have to transform the equation so that it's as if you've measured the oxygen demand of all 300 milliliters. So we find out this 10 milliliters, 10 divided by 300 is 0.033 of the sample. We're going to use that again in a second. And then you would look at the oxygen at the beginning of the test and the oxygen at the end, dissolved oxygen. In this case, in this example, we started out with 9.85 milligrams per liter of DO and ended up with 3.42 milligrams per liter. So we had an oxygen demand of 6.43 with that 10 milliliter sample. And then we have to adjust it. And that's where that 0.033 comes in. We divide that oxygen demand by 0.033 to find out what the oxygen demand was for an entire liter. And what we're trying to get to is milligrams per liter because that's part per million. We can use that in the pounds formula. So this is our BOD. This is the BOD that we're going to use to represent the food coming in. So you see a BOD is not necessarily a direct measurement of food substances. It's a measurement of the oxygen that's going to be required to metabolize the food substances. You can also use COD, chemical oxygen demand. That is a quicker test. Instead of 5 days, you can do it in 4 days. However, you need to calibrate it to your particular plant. Here's an example calibration. This is not a calibration that you can just use on any plant because the chemical oxygen demand, it also oxidizes the non-biodegradable substances. BOD is just looking at what microorganisms can consume, where COD could also oxidize inorganic things that the microorganisms would not even eat, would not consume. So you'd have to know, you'd have to take your COD along with your BOD for a while to get an idea of your particular waste stream, what is an equivalent COD. Now let's look at mixed liquor volatile suspended solids. The mixed liquor suspended solids, that's what we used in the MCRT calculation. It's all of the suspended solids in the aeration tank. The mixed liquor volatile suspended solids, typically between 0.6 and 0.8 or around 70% of the mixed liquor suspended solids. It is used to represent the microorganisms or the biomass. Let's look at how those things are obtained. You take a sample from the aeration tank, from the end of the aeration tank, and you filter it through a 0.45 micron filter that captures the suspended solids. And then you dry the solids and weigh them, okay? And then you calculate the MLS concentration. Now here's an example. We took a 25 milliliter sample and we filtered and dried the solids, and we found out that they weighed 75 milligrams. And there's a little equation that we can use. The net dry weight, which is 75 milligrams, divided by the volume in milliliters, which was 25 milliliters. That would give us milligrams per milliliter. And what we want is milligrams per liter, so we can use it in the pounds formula. So we have to convert that to liters by timesing it by 1,000. In this case, 75 divided by 25 is 3 times 1,000 gives us 3,000 milligrams per liter. So that's how we figure out the MLSS. Now let's look at, there's another step to get the MLVSS. The next step would be to take those volatile solids, to take the dried MLSS solids and heat them in an oven to 550 degrees Celsius, and the volatile solids will burn away, leaving behind the non-volatile solids that are ash. Remember, the volatile solids are probably about 70% of the total solids. So if you look at this, 70% have burnt away, and remaining is about 30%. That's the ash. So you weigh the ash and you figure out the weight of the volatile solids by taking the weight of the MLSS sample before we volatilized it, and subtract the ash, and that will give you the weight of the volatile solids. And then of course we can transpose it to liters, milligrams per liter, just the same way we did with MLSS. So we get volatile solids in milligrams per liter. And let's do a sample calculation here. We're going to calculate the FM ratio for a wastewater treatment plant that has the following data. The plant flow is 3 million gallons per day, and the BOD concentration is 275 milligrams per liter. Remember how we got that? We did a 5-day BOD test, and that represented the oxygen demand of that waste. And our plant flow is 3, so 3 times 275 milligrams per liter times 8.34 is our food. That's how much food's available. The mixed liquor volatile suspended concentration is 2,200 milligrams per liter. That's in the aeration basin, and that has a volume of 1.0 million gallon. So if we look at the equation here, we have 2 pounds formulas. Plant flow times BOD times 8.34 pounds per gallon on the top. The tank volume in million gallons times the mixed liquor volatile suspended solids in milligrams per liter times 8.34. Now, once again, we're not really using the units here. It would be kind of a weird unit if we tried to use units, but we're just looking at a ratio. And the reason for getting this ratio is to compare it to your target ratio. Your plant was designed to run at a certain FM ratio, perhaps 0.3 or 0.35. And when you calculate the FM ratio, you can look at how your plant is performing in relationship to its design ratio. So first of all, let's put our known data for the plant flow and the BOD, and on the bottom, the known data for the tank volume and the MLVSS. We have 2 pounds formulas that we can calculate. We're going to simplify those both. We find out that there's 6,880.5 pounds of BOD coming in each day. And in our tank, we're holding 18,348 pounds of microorganisms to consume it. And we have an FM ratio of 0.375. And so there would be a necessary third step right here. We're just calculating the FM ratio, but the third step would be, well, we're going to compare what we calculated to our target FM ratio. And then we could adjust up and down. If we wanted if we have too much food coming in, well, we can't really shut down the plant flow that's coming in from the collection system, but we can adjust our the amount of solids that we're holding up a little higher by increasing their return activated sludge. If the food is too low, we have too little food for the microorganisms, we could probably slow down that return activated sludge flow and waste a little more and carry less solids to try to adjust that FM ratio. In general, for conventional activated sludge, the FM ratio is 0.25 to 0.45. That's the range depending on the type of plant. It's not going to range that far for your individual plant, but as plants go, depending on how they're designed, there's a range. Basically, conventional activated sludge, you have a smaller footprint, you're processing more food, adding more air, compared to extended aeration, which has a lower FM ratio, less food, more microorganisms, and a lot longer holding time for solids. If you have an FM ratio that's too high, that means you have too much food for the microorganisms to process. So by the time you get to the end of the tank, you're still going to have BOD there, insufficient BOD removal, and poor settling. If it's too low, there's not enough food for the microorganisms to be healthy. So it can promote the growth of filamentous bacteria, can have an unhealthy biome, and also poor settling. And I want you to see a chart here in a second that shows settling characteristics compared to the FM ratio. But basically, what are we trying to do with FM ratio and MCRT as well? We're trying to optimize how well the biomass is removing waste, but also keeping that biomass healthy, helping it to settle well, and also optimize energy use. If you have unnecessary return activated sludge pumping or unnecessary oxygen pumping, those are all things that would unnecessarily consume energy. Also, you see that old sludge there. You're getting into that stage where you're getting different types of organisms that are going to interfere with the settling. Looks like there's rotifers and filamentous bacteria, and there's problems with that sludge being able to settle to a nice, small, compact, dense sludge. So let's look real briefly at sludge settleability, because we're going to look at sludge volume index as a way to operate a plant. So settleability, or the volume of wet settled sludge, is a process of taking a 1,000 milliliter sample, allowing it to settle for 30 minutes. Sometimes this is called the SV30. And then looking at the volume of the settled sludge in milliliters. I'll give you an example here in a second, but we're going to use that to calculate the sludge volume index. So you see in this equation, it's the milliliters of settled sludge in 30 minutes. That's what we just talked about, divided by the mixed liquor suspended solids in milligrams per liter divided by 1,000. So what you're looking at is seeing how well the sludge is settling compared to the solids concentration. And it's that, once again, we're not really looking at a unit-based term here. It's an index that we can compare. So in general, this ranges from 50 to 150 of possible values, really. If you start getting below that or above, you're usually out of spec, but between 80 and 120 is considered to produce the best sludge settling. I'll give you an example here. 1,000 milliliter settleometer is filled with a mixed liquor that has a concentration of 2,400 milligrams per liter. And after 30 minutes, the settled sludge volume is 260. So that's our settled sludge, 260. Calculate the SVI, the sludge volume index. 260 divided by 2,400 milligrams per liter divided by 1,000 gives us this sludge volume index of 108, which means we're right in that sweet spot. And here's that diagram I wanted to show you for each type of treatment: extended air, conventional, and even high rate treatment. There's a little sweet spot where the FM ratio and the sludge volume index are just right. And of course, it would vary slightly for each plant, but the x-axis on the bottom is showing the FM ratio, and for conventional, we're going between 0.25 and 0.45. And that little yellow spot that I indicated there is probably between like 60 and 120, something like that, on the sludge volume index. And you see that red line shows that that's probably the densest little part where the sludge is going to settle to the smallest amount of space. So you can actually operate your plant based on what produces a good sludge volume index. And our last poll for today, you can indicate by sharing the letter. The wastewater coming in to an activated sludge plant has a dramatic and a sudden increase in BOD. So you have a lot more BOD coming in suddenly. Which of the following would best help the operators ensure there is sufficient biomass to provide optimal treatment? And just share the letter of the one that you think is the best.
I'm seeing a little bit of a mixed bag here, seeing some D's, a couple of E's, a couple of A's.
I think we have some comedians in the.
A bunch of A's are starting to roll in now.
As you can see, the FM ratio would, if you have a sudden increase in BOD, you have more food. And so we want to maintain a certain FM ratio for our plant. So we'd want to figure out what is the required MLVSS that we need, and then we'd probably adjust the return activated sludge flow to start increasing that. So today, we looked at a couple of activated sludge layouts. We looked at the FM ratio as a calculation that we can use for process control, the MCRT, the mean cell residence time, and we talked about return activated sludge flows and waste activated sludge flows as means to adjust the activated sludge flow process. I included in your handout some sample problems for some of the problems that we didn't really have time to get to. I'll share my email for anyone that wants additional resources about some of these calculations and about the pounds formula. I want to also mention that the efcnetwork.org site, there's lots of resources. For example, this page, you can click on your area or state and get sources of funding that you can explore and contact. Lots of resources on that. Also, I wanted to share the Environmental Finance Center Network website, and also the Great Lakes Environmental Infrastructure in Region 5. That's our website. And if you would like to contact me by email, gpearson@mtu.edu. You can also schedule a technical assistance meeting with me, or even connect with me if you'd like. And that is in your handout. You should have the slides as a handout. Reference guide is a handout that has quite a few manuals and formula sheets. And I want to open it up for any burning questions that we have that we can answer in the minute or so we have left. Thank you for attending today.
All right, there are a few in here, so really quick, we'll do as many as we can. And like Greg said, his email is in the slide deck, so any questions that we don't get into, please feel free to reach out about them. But I'll start here. The first question asks, when would you use extended aeration versus conventional activated sludge?
Yeah, it's a good question. That really is an engineering design issue. The extended aeration has a bigger footprint, so so that's one of the aspects. A bigger footprint, so you have more land. It's probably a rural area where there's not such dense building, and you also are carrying a lot more microorganisms. So your food loading is a lot less, and it can handle shocks a little bit better because you have a long time and a lot of microorganisms. So it's a little more resistant to problems. I would say extended aeration is probably preferable from an operator standpoint because every move is not so critical. Because you know the solids are in there for 20 to 30 days and the aeration time is 18 to 36 hours. You have a little more room. I won't say air, that's probably not the right. You have a little more flexibility to make adjustments and not end up with major problems. I'll say it like that. Whereas a conventional plant, it's very fast moving and it's meant to process waste efficiently and quickly. And you make an adjustment, you know, it has to be the right adjustment more so than extended aeration.
All right, thank you. And then we'll just do one more here. This question asks, how does the return activated sludge and waste activated sludge get separated?
It's just two separate pumps, and you know, you're pumping out of the same reservoir. So yeah, there's no separating it. It's the same sludge. It's just how the speed at which you run each pump.
All right. Well, thank you, Greg. Thank you for sharing your expertise with us today. Like Greg said, of course, follow up with any other burning questions that you have that we didn't get to. Following this webinar, you will receive a follow-up email with the slides from today and a link to the recording. We also ask that you complete the webinar evaluation following this webinar so you can let us know your thoughts on today's session, as this helps us plan future webinars on topics important to you. So thank you again, Greg. Thanks everyone, and we hope to see you again at future EFCN events.
Thank you, everyone. Thank you for your participation today.